Back. So, continuing our series, last time we left off discussing the loss function and how we minimize our loss function during regression. And today we're going to discuss regularization, specifically Lasso and ridge regression, and motivate what complexity and overfitting are in models. So, let's dive right in by getting back to where we left off. So here we have our loss function, which tells us how much error we have, which is the predicted value minus the the real value minus the predicted value for each data point squared, summed over all data points. And what we said was that we wanted to minimize this value of the loss function by tweaking beta. Therefore, tweaking the parameters in our function so that we would have the minimum error over all data points. And that's great. At first glance, it might seem like our work is done. We've found the best possible model given our data. But the real world is a little more complex than this simple model. And what we find is that when we fit a model with some set of training data, meaning that we find the optimal beta parameters by fitting the model, and then we try using that fitted model on some new data that we've never seen before, it might not do so well. And the reason why this happens is because the model learns the training data and all of its nuances too well. And that sounds kind of ridiculous that I could learn it too well, but that is what it does. It actually overfits to that data. And it learns the nuances particular to the training data that might actually not generalize over all the data. And therefore, it learns that data too well and it overfits. And how can it learn nuances that are particular only to the training data? Well, we have to remember that the training data is just a sample of all of the real world data. And whenever you sample something, you choose a subset of it, and you always end up creating some nuance just by random chance. And you don't want your model to pick up on those nuances that were generated just by, the sampling effects of having a training data set. With that said, we don't want to learn our sample too well, or we won't be able to generalize to the real world. Let's try to convert this knowledge into mathematics, this intuition here. Let's quantify it using our math. And this is where things get a little hairy. So let's recall our equation once again, and that would be the equation for our model here. And now let's ask ourselves a question. What is it in this equation that allows the model to learn? So how do you define the learning in this equation? So the y is the predicted output. The x1, x2, x3 are the features of a new data point. The beta 3, beta 2, beta 1, and beta 0 are what our model fits to define how much impact and in which way the impact of each feature impacts our prediction. So really, it's our betas that define how our model has learned. And they also define really the complexity of our model. So the larger the betas, the more impact the features have, meaning that the model is more complex. and the output is more impacted. So a larger beta impacts the output more, meaning that our model is more finely tuned and more complex. Now, let's recall what our beta vector was. So let's have that here. Our beta vector is just, the individual betas packaged into a nice form, and that's it. So with that said, let's keep that in mind. Let's try to quantify now the complexity of a model. And the simplest way to do it, let's go back here. I'm just going to take the betas and add them up. And I'm going to say that that's the complexity of our model for the sake of what we're doing here. And I'm going to put that right here. So the complexity of our model is just the sum of our betas. Beta 0 plus beta 1 plus beta 2 plus beta 3. Now, this won't work out exactly as we hope for it to. And why not? What if our beta 1 and beta 2 have the same value, just that one is negative and one is positive? So let's say this is negative 10 and this is positive 10. Then the complexity would add to 0. They just cancel each other out, even though they're really impacting the model a lot in different ways, because the beta 1 is going to be associated with one feature and the beta 2 is going to be associated with another feature. We don't want that to happen. So really, we're looking to not have things cancel out. Also, a negative beta does not mean that it reduces the complexity. So really what we're intuitively getting at here is the magnitude of the betas. That's what we want to use to define the complexity. So let's do that. So our complexity now is just going to be the sum of the magnitude of the betas. And this magnitude symbol just means that you take the positive, or the distance from 0. So if it's negative 10, it would be positive 10. If it's positive 10, it remains positive 10. And so that's one way to deal with, the negative issue. Another way to deal with the negatives issue is to recall that when you square things, they always take a positive value, unless they're imaginary, and we're not dealing with any imaginaries here. So we can just square the individual betas and sum them and define that as our complexity. And both of these will work. And that's fine. And that's great. And we'll see how these are used in a few moments. So, with that said, excuse me for 1 second. Okay. What we want to do is now use this complexity in our original equation and somehow modify our equation so that it doesn't become too complex. Or in other words, we're going to use this complexity as we've defined it to minimize overfitting. So what we do is we actually just add what we call a penalty term. And before we go there, just one last thing. So the sum of the magnitudes of the betas here can actually be rewritten as the magnitude of the vector beta. That's the definition of the magnitude of the beta vector. And very similarly, the sum of the squares can be written as the square of the magnitude of the beta vector. And so there we now have very simple terminology for what we're trying to quantify here, which is the complexity. We can either quantify as the magnitude of our beta vector or the magnitude squared of our beta vector. All right, so with that said, now let's take this complexity, or these definitions for complexity, and incorporate them into our model. So let's keep them right here. Let's get rid of this. And let's do it in the simplest way possible. And let's take the first definition of complexity that we have over here. And we're just going to add the complexity of the model to our earlier loss function. So now what we're saying is that we're going to minimize beta, and really the minimizing of beta is over everything here, everything that we see in front. So we want to minimize now this whole function when it relative to beta. And what does this do now? If beta is too large, meaning our model is too complex, then we are penalized because the magnitude, the sum of the values of the betas, goes up, and then our model will not want to, the minimum of this value will no longer be minimized for such large betas. So then we'll be forced to shrink the values of our betas or to reduce the complexity of our model. And so this is known as penalizing the loss function. So we're adding some penalty term. Now, in addition to that penalty term, we also want to add some sort of knob to control how much we want to penalize things. And so all we're going to do is we're going to add a parameter here and multiply it by this beta. So let's do that. And we added a lambda. So this lambda is a tunable hyperparameter that when lambda is 0, this term just drops and we're left with our original optimization that we saw in the last video. But for very large values of lambda, we start to heavily penalize for larger beta values, for more complexity. And for a lambda value of infinity, what you can convince yourself of is that all the betas would be forced to 0. 0 would minimize the equation if lambda was infinity. So there we have it. This is called a Lasso regression. And so we can also perform this in a different way. Instead of using beta, we can use beta squared, which is the other form we had for measuring the complexity. And now we minimize this whole function. We add a penalty term to our loss function with lambda times beta squared. And this is ridge regression. Now, these two formulas can be derived mathematically. I give a much more intuitive way of deriving them, but regardless, they work. People have tested them on real-world data sets, and this method for reducing overfitting is successful. And simply by penalizing the complexity of the model, you create a model that can better predict outside of the training data set. But that's, of course, only when you tweak this parameter lambda to the appropriate levels. So this has to be optimized properly, or hyper-optimized. It's a hyperparameter. So you have to tweak it until you figure out where it best serves the purpose of minimizing overfitting without losing too much information. Now, let's take a look at these equations and how they differ when it comes to actual optimization. So what is this lambda beta and this lambda beta squared doing? And so let's do that over here. And let's motivate this with an image. So what we have here is a diagram where we're showing what the Lasso and rich regression penalization terms do. And so what we're looking at here is that the axes here represent the values of beta. And so we're looking at the possibility space of this complexity factor in both of these images right here. So this is a two-dimensional plot where we're assuming we only have two features in our data set that correlate to, or I guess one feature if we have a beta 0 that's not associated with the feature. And things obviously get much more complex. You can have very high dimensionality in your data set. But here we have two betas, unlike the 4 that we had in our example before. Now, here what we see is what you get when you fix the magnitude of beta to a fixed value. So you fix the magnitude of beta and the possible values of the two. So remember, the beta vector, the magnitude of beta, is beta 0 plus beta 1 in this example, since we have two dimensions. So all the possible values of beta 0, let's say beta 0 is on this axis and beta 1 on this axis, all the possible values for beta 0 and beta 1 fall along this red line that's formed here. Now, in contrast, here we have, again, beta 0 on this axis and beta 1 on this axis. But the red line here, the circle, is the values for which beta 1 squared plus beta 2, or beta 0 squared plus beta 1 squared, sum to a fixed value. It would create a circle. And that makes a lot of sense. That should be reminiscent of the equation for a circle. X squared plus y squared equals the radius squared. And so that's what's going on. That's why we get a circle here. And now this is embedded into, so the axes here represent our possible beta values. And we're going to have some other function, which is the optimization. This is going to be the loss function. And there's no good way to represent what the loss function looks like. So we just have like a toy example, right? But what we see here is that when you have the magnitude of beta squared, you don't know where your loss function will be minimized on this surface, this circle. Same thing here. You don't know exactly where your loss function will be minimized on this surface when we're using the magnitude of beta as our complexity factor. But because of the shape that this takes, what we find is that the corners tend to most often minimize the value of the function because they lie farthest out from the center in terms of magnitude. So this point has a much larger magnitude from the center than this point, even though the sum of the betas add up. That's not true here. Here, all points on the edge of the circle lie the same distance from the center. And so here, this is sort of a graphical, intuitive uh, motivation for why what happens is you end up picking points on the corners here, and points on the corners here actually correspond to locations where one value of the beta is set to 0. So on this axis, so if this is beta 0 and this is beta 1, at this point the value of beta 0 is 0. And at this point over here, the value of beta 0 is 0 as well. And conversely, the values of beta 1, which is this axis, at this point and this point are 0. So optimizations will very often set some of your beta values to 0. This is why Lasso regression is said to perform feature selection, because it sets some of your betas to 0 and it discards them for you in a certain sense, if they're not impactful enough that the model would deem them important enough to be considered impactful yet not detrimental from an overfitting sense. So it's kind of a balance that the model is achieving. And so I think that's it. So there's really not much to expand on here, but now you get a motivation of what overfitting is, what complexity is, why we add these penalization terms to our loss functions when minimizing, and that is what regularization is. All right. Thank you for tuning in. Till next time.